boson says why, ponders the question of why do we have mass? So I didn't show you the equations of particle physics and the Standard Model, but if you try and put the masses of particles in directly, and particularly the masses of things like the W boson, the weak force, it just breaks immediately. You get infinities whenever you calculate it. It's embarrassing, but it's just rubbish. But the theory was so good, right? So the theory works for everything else, and when I say good, it can predict things to 1 part in 10 to the 9 or something. It's a ridiculously good theory, the best that man's ever had, probably. So about 6 scientists, including Peter Higgs, so this is taken years ago, he looks old, and he now looks the same. You kind of, as you get older, you just reach this stage, and that's it. You don't decay any more than that. You just stop one. So he proposed this idea that you have a field that fills space, and you interact with it to get mass. So it's not like you have mass intrinsically, or at least for these particles, it's not like they have mass intrinsically. They interact to get their mass with a field. And the idea of interacting with a field isn't actually alien to you, because you've probably seen the field lines around a bar magnet, for example. And you know that's because the iron filings, if you've ever sprinkled iron filings around a bar magnet, it's because they move because of the field, so they're interacting with the field. So that's kind of, this idea isn't wacky, it's not something you should throw in the bin immediately. So I'll explain how it works. And if you imagine there's a party of physicists, and you'll think, well, this doesn't happen. It does. I actually missed most of the party on Wednesday because I was being interviewed by Sky News, and I got back, and it wasn't even like the booze had gone, right? They still had alcohol there, but they wouldn't open it. They said, well, we're not allowed to open it after 8 o'clock. I said, but we've discovered the Higgs, and there's a beer. Can I really not have that? He's just put it in. Terrible. Okay, so you have this party of physicists. In comes a celebrity, and for them it has to be Einstein. Einstein is, of course, now a ghost. He has no mass. And people, obviously they want to talk to Einstein. They still don't know how to put gravity into particle physics, despite the fact that he was working on this before he became a ghost. So they say, look, have you come back to tell us something? How did you rise from the grave? What do you know? And so they cluster around him. Now he's trying to get to the drinks table with the sloppy man in the conference centre who won't give him a beer. And he can't get there because people are crowding around him and flocking around him. Right? So it's like he has mass. Right? He has an inertia. It's like he has a mass, and that's what our particles do. They interact with the Higgs field, and they get their mass. So I'll explain what the Higgs boson is. Fields, when we have fields, I said that they have a particle associated with them. So in the electromagnetic field, it's the photon. The photon is the particle of the electromagnetic field. And you should really think of this as like you're thinking about the same thing in 2 different ways, right? Fields came about because in the Victorian era, when they were thinking about electromagnetism, they had a very mechanical view of the world. So the idea of a field of cogs that things interact with was very attractive to them philosophically. The idea of a particle is somewhat different, but it's the same thing you're talking about. So imagine that there is no Einstein now, but there's a rumour of free wine, right? And so these people start chatting to each other. And what we've done is we've excited the Higgs field, and it's like there's a little particle, which we can call the Higgs boson, which is one big around. So the boson is an excitation of the field. Have you read anything about wave-particle duality or anything in quantum mechanics? Some people nodding, some people not. Okay, so that's really what this is related to. Things sometimes behave as waves and sometimes as particles, but really that's just 2 incomplete pictures of a fundamental object that we just can't grasp properly. And that's what we're dealing with here. Right, breaking news. CERN has discovered a Higgs-like particle. Right. The reason that, you'll notice there was caution in the way that we worded this. We didn't come out and say we discovered the Higgs boson, right? And that's not because we don't think we discovered a new particle. We definitely discovered a new particle. Both experiments see enough evidence to say that there's something absolutely new in nature that we've never seen before. And actually, if you look at the properties of this thing, it's almost exactly like the Higgs boson. In fact, it probably is the Higgs boson. It decays to photons, right? The photons come in, they make a Higgs, it decays to photons. Some of the time, it decays to Z bosons. You'll get a pair of Z bosons, right? And we've seen this, and the amount of time that it decays to each of these things is about the same as we'd expect from a Higgs boson. So I think if you ask 99% of physicists, there's always 1% that have to be different. If you ask 99%, they'll all say, yeah, look, it's the Higgs boson, it obviously is, but you don't make that kind of announcement when you're first doing it, because if you did do this, and then a year later you went, oh no, sorry, it was a packet of crisps or something. You'll look dead, so that's why we do it. There's another reason we're being cautious, and that's because the Higgs boson solves one problem in the Standard Model. It explains where mass comes from. It doesn't explain the other problems, right? It doesn't explain why there's all these weird masses. If you look out into space, everything that you can see in the universe is about 4% of the density of the universe. There's this weird dark matter which is filling space, and we can see it interacting gravitationally. If you watch galaxies go around each other, they move in weird ways because there's obviously some extra mass there which we can't see. We don't know what that is, and we want to discover that at the LHC. So the hope is that we have some extra theory which is beyond the standard model, but we're going to discover more details at the LHC. And if that were true, there might be more than one Higgs boson. Right? The standard model says there's one Higgs boson, there it is, that's what gives you mass. Supersymmetry would have at least five Higgs bosons. So we might be seeing one of them, and there's others there, and as we accumulate more data, we'll see them. There's also clues in the pattern. When I said that when you look at how often it decays to photons, or how often it decays to something else, there's clues there that you might be seeing something which isn't the standard Higgs model, standard model of Higgs boson. There's just tantalizing hints that it's decaying to photons more often than it should. Right? And that's very significant because it tells you that there's something else there. There is another discovery just around the corner. And this isn't even us saying, you must give us much more money because we have to keep doing this work. It really does look like there's something strange going on. And I hope that persists. What happens is when you first discover these things, you have very large errors. You know, you've plotted graphs with error bars now, presumably. Someone's introduced you to the concept of an error bar. You know, you don't know anything precisely quantifying what error is. So the error on the rates of decay to photons is currently quite big, but I think it looks like there's something strange going on. And I hope it persists. It would be a lot of fun if it did persist. And if not, we get this amazing particle. You can study it in 10 years anyway. So there's one particle called supersymmetry,